What's good, YouTube? It's your boy Musa back with another video. Today we have another Bollywood song. I'm not even pronounce the name of the song. I'm not pronounce the name of the people because I don't like to insult people, so I'd rather just not do it. We're gonna get right into this. Let's do this. Let's go. That's just like a full-on party. It looks like they're full-on raving out there. She got low.
Good afternoon, everybody. Welcome to this last week experimental testing for aerospace structures. Indeed, this is the last week that we are going to have together, and then I will meet you all during the final exams. By the way, I still don't know the way we are going to give the final exam. Up to now, it is distance, so will be done using both exam.net and Google Meet. Please remember to have at least 2 smart devices in order to connect with the exam.net and then in order to video recording what you are doing while taking the exam. Okay. The exam will be, as I promise you, an oral one. That is, you are going to answer using a written form of some oral questions, okay, that you find out in a text available at the link that I give you before the exam on the exam.net platform, okay, website. Okay. Today I'm going to upload the last Friday class. I completely forgot that, and laboratory activity number 4. And at the end of the week, so by Friday, I will upload laboratory number 5. Okay, so feel free to watch this recording. They should represent what you could have done if in-person classes were available. I'm sorry for that, but the COVID didn't allow me to enter in the laboratory, and because you are not staying, all of you in Rome, this video recording is the only solution that I got at this time. Okay, so let's start this final week. Our class will end this Friday. And our week will start with the comparison between the numerical and experimental models. Last Friday, we saw what we call the direct comparison between the natural frequencies and the mode shape. Then we went through the orthogonality check in order to have a different way of assessing the correlation between modes and your numerical models. Okay. Then today we are going to discuss a little bit what is the mode confidence check. The mode confidence check is a way to represent the idea that if 2 mode shapes are representing the same mode shapes, those mode shapes should be parallel. Okay, and therefore this mode confidence check is introducing an analytical number, an analytical parameter, if you want, that is telling you what is the degree, so what is the confidence of your model mode. Okay, let me enter. Okay, so this mode confidence check, as I said, is carried out using some parameters, some numbers, and these are two actually. These are called the MSF, and the other one is called MAC. Okay, the first acronym is for modal scale factor. Okay, and the other one is called modal assurance criterion. Okay, now let's talk about the mode confidence check. Okay, carried out using the mode scale factor. So the mode scale factor is telling us what is the degree of proportionality between two modes. Okay, so if two modes are representing the same mode shape, then they must be proportional. Okay, and that is what's behind the modal scale factor. What does it mean then? The modal scale factor is telling me that the modal scale factor between mode I and mode J is a quantity that is just representing you this ratio. So your whatever mode I transpose times whatever mode J, okay, divided by whatever mode I once again transpose divided by the same mode, multiplied by the same mode I. Okay, so first remember, mode shapes I and J are defined upon the same degrees of freedom. Okay, otherwise it could not be the multiplication could not be carried out. Okay, second, the weighting matrix W, okay, is used to different weight mode components. Sorry. Mode components. Okay, and this W weighting matrix is in between the two modes, generally speaking. Most of the time, this weighting matrix is an identity matrix. Okay, otherwise, generally, the W matrix, the weighting matrix, is a positive definite symmetrical matrix. Okay, what is the meaning of that? In order to give a representation, to let's see, discuss a little bit this formula in order to have a better memorization of that formula, please consider, if you just to set aside, okay, if you are considering two vectors v and u, for example, okay, and if u is parallel to v, then what you can say is that your u vector could be set equal to a parameter, okay, alpha times your vector. Now, by projecting, oh, projecting into the vector v, for example, what we got here is u scalar v, okay, is equal to alpha v scalar v, and therefore what you got is that your alpha, the proportionality term between these two vectors u and v, is given you by u scalar v divided by v scalar v. Okay, that is just the formula that we use so far. Okay, so your modal scale factor is the proportionality constant between these two vectors. Now you can easily understand that if you're going back to the use formula, your mode sheet I is representing your numerical mode and J is the corresponding experimental mode, then you are just finding out what is the scaling constant, the scaling factor between the numerical and the experimental one. Okay, so if your I mode is your, let's say, numerical one, and your J mode is the corresponding experimental one, then the modal scale factor between I and J is the proportional constant of proportionality. Is the constant of proportionality between the corresponding numerical and experimental modes. Okay, please note that these two modes, phi I and phi j, are assumed to be parallel. Okay, otherwise that modal scale factor is not having any meaning at all. Okay, because the way the modal scale factor is defined is just by using this formula that I wrote you in green. Okay, and thus we are assuming that these two modes are parallel. So you can identify the scaling factor between the numerical and the experimental modes once you are quite sure that your modes are parallel, that is, are the same. Okay, now the second index that we are going to consider is the model assurance criterion, MAC. Okay. Model assurance criterion. And this model assurance criterion is defined quite similar as the previous one, but the meaning is deeply different. So let's consider this index model assurance criterion between two modes I and J as as the ratio between the amplitude of the inner product between the I mode transpose times the J mode, okay, and this amplitude square divided by the inner product between the I mode America, I mode, okay, times your J mode, sorry, not America, transpose. Transpose. Okay, and if you would like to give different weights to different components, you have just to add, better introduce the weighting matrix as we did before. Okay, that is what we got. Okay, and the interesting thing of this new index, the model assurance criterion, is that this value, the MAC value between these two modes, is a quantity that is defined in a 0-1 range. The 0 means that there is no correlation at all between modes I and J, whereas we have a perfect correlation, once again, between modes I and J. Okay, and that is quite interesting index because just tell me what are these two modes, and then I can tell you if those modes are parallel or orthogonal. They are orthogonal if this MAC index is equal to 0. They are parallel if that index is equal to 1. What is the origin of this index, of this MAC index? Now let's consider again two vectors u and v, whatever they are, and if I consider the inner product between these two vectors, this inner product, as you know, is equal to the amplitude of the vector u times the amplitude of the vector v times the cosine of the angle beta between these two modes. Okay, let me have mode u like that, e like that, and therefore this is your beta angle. Okay, now if we consider the cosine square of this angle beta, that is equal to u times u, that is the inner product between these two vectors square, divided by u square times v square. And actually, I should have written here the consistent ample sign. Okay, so we can have an information of how well correlated is the numerical model with respect to the experimental one just by evaluating the difference between the natural frequencies, okay? And if you want to check those differences, and you can have a direct comparison just by putting on a plot in the y-axis these two different natural frequencies and see what is the shape of the regression line that is passing through this point in this natural frequency domain. Okay, you are expecting a slope of this regression line that is equal to 45 degrees. If not, there is an error, as we said on Friday, and the error is a systematic error. And all the deviations between this point and this regression line is representing your random error. Okay, you can go through and therefore to check also the orthogonality with respect to your model mass. Okay, and finally we have a chance of evaluating with just a number how parallel or how orthogonal these two modes are just by evaluating your Mach value. Okay, this Mach value is defined as I wrote here. You can also include a weighting matrix. Once again, W is the weighting weighting matrix between components. Okay. And if you are having a number that is close to 1, that means that your mode shapes are practically parallel, and therefore the previous identified value of the model scale factor MSF is telling me what is this proportional constant between these two modes. If the Mach value is not unitary, is very, very low, let's say is close to 0 value, that means that your mode shapes are practically orthogonal and your modal scale factor has no meaning at all, okay, because the modes are, the considered mode are orthogonal. If you remember, we also made a direct comparison between the mode shapes, okay? If I recall this representation like this, so I consider two corresponding modes. So in the x-axis, I'm putting your components, okay, of your I modes. In the y-axis, I am putting the corresponding components of your J mode, and maybe your, let's say, your components are placed in that picture so that they are looking like this, and in red here is a dashed line. I am writing a possible regression line. Okay, so just to give you an idea, the slope of this regression line, okay, is your model, is representing your modal scale factor, whereas distances between the points and the regression line like this, okay, are representing the information of your Mach value. Okay, so just to give you different representations, different representation of what we have just defined in terms of modal scale factor and modal assurance. Okay, just one last thing about the comparison. Sometimes you have to compare mode shapes that are complex mode shapes, and you have to compare those mode shapes with the ones coming up from the numerical analysis that are, generally speaking, real mode shapes. So how can you compare these mode shapes? Okay, you can compare these mode shapes just by projecting your mode shape into your real or imaginary axis. Okay, let me show you this. So generally, your experimental mode shape, whatever it is a complex quantity. Okay. Please know that the proportional damping is just our idea. The true system is not knowing anything about proportional damping. So what we got here is just an experimental mode shapes. That is what we got straight from your, let's say, complex exponential method, hybrid time domain technique, or whatever other technique. Okay. So comparison is carried out between real mode shapes from numerical analysis generally and complex mode shapes from experimental investigation. Okay, so that is what's happening in general speaking. So what we got here is just how to, let's say, realize, okay, complex mode shapes, or in other words, how can I represent a complex mode in the real world? Okay. Now, generally speaking, if damping is not that large, then what we got is that modes are practically real. Okay, what does it mean that? Let me plot once again your whatever shape, but this time in a real and imaginary, in the complex space on the real imaginary axis. Okay, so here I'm putting my real part of your I mode components are, okay, and here I'm plotting your imaginary part of the same ith mode corresponding R components. Okay, so what we got here, for example, could be something like that. Okay, these are possible pairs of your whatever mode. Okay, as you can see here, if you check for, let's say, one point of this plot here, for example, this point is representing the complex component of the mode. Okay, but and therefore you can see that these components are actually complex numbers. Okay, but if you draw sort of regression line between these components, generally what you are having is something like this. Okay, so as you can see, if you define a new mode constant, okay, that shifts, that rotate, okay, the components of the mode by the angle, okay, let me call that your phase, okay, of your complex mode, sorry, of your complex mode here. Okay, then what we got here is that all the components could be laid down in the real axis, and therefore you are just viewing at this complex mode as a real mode. Okay, um, so what you have to do is just finding out what is the phase angle of this mode, and therefore rotate the components by that angle. Okay, this angle, by the way, is called the phase of the mode I, in this case, or the phase of. Okay, so your whatever component of your, sorry, whatever component R of your mode I that is represented as a real quantity, yeah, could be viewed as the amplitude of the corresponding R mode of the same I mode, but this time viewed as the complex quantity, so the amplitude, times the sine, sorry, the same function of the cosine of the phase of such a mode. Okay, sorry, R of the I mode complex. Okay, and there you go. Just by projecting the components into the real axis, you got the imaginary, so you got a real representation of the mode. That is, you realize your complex mode. Be careful that you can project those complex components not only on the x-axis that is on the real axis, but also on the y-axis that is on the imaginary axis. And that is dependent on what are the components like. So you can have a quadrature realization or in phase realization. Okay. This approach, this method is quite good, okay, because if when we are dealing with a condition like that, that is, you are considering a light damp structure, structure to be to which correspond a practical real mode. Okay, sometimes that is not possible to apply because the modes are really complex. Just because there is a damping mechanism that is bringing into the structure a lot of damping, and that is not the way that we are considering as light damp structure, and therefore the mode is fully complex. In that case, you have to apply other approaches that, because of time, you're not going to see this year. But I think that for you, it's enough to understand that your mode for whatever estimating technique is coming out as a complex mode. If you want to compare this mode with a mode coming out from the numerical analysis, then you have to have it in a real form. That is, you have to realize that. And in order to do that, you have just to apply a projection criteria on this complex mode. Be in mind that this complex mode is actually a practically real one, because there is just a common phase angle between components, mode components, that allow you to rotate those components into the real axis. Please note that this rotation is just the equivalent to say that I am considering a complex scaling factor for that mode that is bringing me to the real axis, almost to the real axis. Okay? Questions on that? Okay, so if there are no questions, let me enter, once we cover some basic topics in numerical and experimental correlation, let me enter into the methods, into the issue of trying to find out a way of understanding where to change your numerical model once you find out from the experimental findings that the Mohs shapes, the numerical Mohs shapes, natural frequencies are not just the ones that we have estimated in your experimental analysis. Okay. Remember, when we were dealing with the direct comparison between Mohs shapes and also between natural frequencies using a plot, then we were also discussing the fact that if there is, for example, we're referring to the difference between the natural frequencies, we are discussing the fact that if the slope of the regression line is not 45 degrees, that means that there is an error that could be easily found out just by changing, for example, the Young modulus or the distributed mass of this structure. Okay. However, it is not always that easy to try to reduce the error between the numerical and experimental model, and that's the reason why some methods were developed in order to have a procedure that automatically tells you, tell you what is the point of the finite element model that or the area matter that has to be refined, and what is the magnitude of this change in the structural properties that is capable to bring a very sensible reduction in the difference between the numerical and the experimental model. Okay, these methods are co-updating methods. Okay. And these updating methods are defined in the finite element model analysis. Okay. So once again, we are having your very nice numerical model, very large mass and stiffness matrices, okay, that is giving you the model properties of your whatever structure, whatever system, and then you compare these model parameters with the experimental ones. If you are lucky, this comparison is good for you. That is, if you are lucky, the MAC, for example, is very, very high, close to, let's say, 100%, that is close to unit value. The errors in frequencies are quite close, let's say less than 2-3%. Okay, if you are getting this condition, then you are very, very happy. But if either the MAC or the natural frequency shift is not that good, then you have to change your numerical model. Then you have to change your finite element model in order to reduce the gap between the experimental and the such a numerical model. Okay. First, I would like to discuss what are possible causes for such inaccuracies that we discussed about. Okay, why this method, numerical method, is not giving me the same results as the experimental ones. Okay, possible causes for such an inaccuracies in the finite element model could be the one that I'm going to tell you. For example, boundary condition representation. Maybe the clump n is not the clump n, Fresnel clump n in the experimental one, real world. Okay. Discretization. Maybe you need to consider a final finite model with respect to the actual one, just because maybe it's too stiff or some part of the structures are not behaving from the dynamic point of view as the experimental one. You have to consider some modification in the material properties. Okay. And then there are some other issues that are brought to the system because there are some junctions, maybe some free plays. There are some bolts and other connecting parts, okay, that are not very well modeled. And if they are, maybe they are bringing in some non-linearities. I'm talking about, for example, free plays that are not covered when you are describing your system in a linear model. Okay, so these are just a few because there could be also other causes that are bringing some differences between your experimental model analysis and the one that is numerically carried out. Okay, these methods that are the methods that are developed during the years are based on many approaches. There are a lot, but what I'm talking about today is about the first, if you want, method that has been developed, and this method is called EMM. That is the acronym for the error matrix method. EMM. Okay, and this matrix, error matrix method, EMM, is trying to find your error mass matrix, your error stiffness matrix, and in general, your error damping matrix, so that your updated U mass matrix is given you by the starting numerical mass matrix plus this error mass matrix. The same for the stiffness, so the updated stiffness matrix is equal to the starting point numerical stiffness matrix plus this error matrix, this error stiffness matrix, and your updated damping matrix could be obtained by the starting point numerical damping matrix plus the error damping matrix. Okay, so the error matrix method is a method that is trying to find those error matrices. Okay, error matrices with respect to the mass, stiffness, and damping. And these matrices are the updated matrices. Okay? And of course, these numerical matrices are the numerical from final element model initial matrices. Okay? So the error matrix method is just trying to find out those error matrices so that you can have the updated matrices in your final element model. Okay? So the updating process, the EMM updating process, okay, is divided into two phases, into steps. Okay, the first one is called error localization. That is, find your delta K, delta M, and so on. Okay. Then second step is the model updating itself. Okay. That is, find the updated mass and stiffness matrices, okay, using the error matrix that you got so far. Okay. Is that clear? Okay. So yes, we are on time, 3 p.m. So let's have a break for, let's say, 10 minutes at most, and then we resume the class. Okay. So be back by 3, let's say 10 earlier. And of course, if there are questions, I'm here, please.
Professore, scusi,
Sì?
una domanda. Lei ha detto che gli autovettori che otteniamo dall'analisi numerica sono reali, ma questo nel caso in cui utilizziamo un modello di smorzamento proporzionale?
Sì.
Perché...
Sì,
Ok.
sì. In genere considera che dall'analisi numerica si prende praticamente sempre il modo reale, ok? Si aggiunge lo smorzamento, uno smorzamento anche viscoso, oltre che di steresi, però per problemi di risposta in sé, ok? Quindi per problemi di risposta dinamica. Ok?
Va bene, grazie mille.
So your colleague were asking for a confirmation about the numerical modes that are considered always real. That is true because generally from the normal mode analysis in the finite element model, you are not including any damping at all because that damping value is having a lot of uncertainty. Okay, so generally the dynamic model is when referring to model parameters is just a real one. Okay, and then the damping is also added in the numerical analysis, but mainly for response problems. Okay, so for dynamic response problems, in order to see what is the amplitude of a response for a given frequency, in order to have a frequency response function characterization of your system. Okay, but that is if you want, damping is added afterwards. Okay, so first there is the validation of your dynamical system through mode shapes, through model eigenvalues and eigenproblems, okay, vectors, okay, without any damping at all.
नशे सी चढ़ गई ओए कुड़ी नशे सी चढ़ गई पतंग सी लड़ गई ओए कुड़ी पतंग सी लड़ गई नशे सी चढ़ गई ओए कुड़ी नशे सी चढ़ गई
This looks really interesting, man.
पतंग सी लड़ गई
Where is it? Because I don't know. Where's the location? Is it like we're just dancing around and everything? It looks like, then again, you can't really see anything. It looks like they're standing next to a bridge. That's a bridge in the background, right? Yeah. UK? No, I see a. Oh wait, I think I saw a French flag. French flag in the back. Oh, it's France. Yep, I can see it. I can see the gold things as well. This is Paris. Damn. Okay, it's Paris. I've been here. Okay, so that's how we're dancing now, yeah? This guy has an amazing voice. What's his name again? I can't pronounce his name, but it's the guy with the A. I can't pronounce his name. Ajit Singh? Because the H is silent, right? Ajit Singh. I don't know, man. I'm probably pronouncing it so wrong. Where are all these thingies coming from, though? They're fully raving up in just Paris, just like this, you know? Okay, cheers. Drinks up. I've never understood that, man. We're drinking like that and then they put the lemon and they're all going pulling all these faces like, oh, this is very nasty. Why you put yourself through that shit? That looks very uncomfortable. Okay. Chorus slaps. But I like to see, the one thing I like about like a video like this is when there's so many cultures, so many people from different backgrounds all blended up together, having fun, just enjoying it, good man vibes. I love that.
गई ओए कुड़ी लहू में बढ़ गई कमली कहानियों सी जंगली जवानियों सी जमती पिघलती है पल पल पानियों सी बहती रवानियों सी हंसती शरानियों सी चढ़ गई हम पे बड़ी मेहरबानियों सी ऐसे खेचे दिल के पेचे गले ही पड़ गई नशे सी चढ़ गई कुड़ी नशे सी चढ़ गई.
Here comes the wind, man. I knew he was gonna come through eventually.
Look
at him. Harris ain't that windy.
पतंग सी लड़ गई ओए कुड़ी पतंग सी लड़ गई.
Oh, nighttime party. So what did they practice the whole night, fam? Is this like a whole night rave? I'm finished.
कन्नियाओ कट्टे कदी बन्नियाओ टप्पे कदी दिल दे चौराहे लंघ दी.
He's got his hands in his pockets, acting all cool.
हंसी कदी ठट्ठे कदी.
Who normally what woman do you know that stands like this?
हंसी कदी ठट्ठे.
No woman stands like I'm finished. Ain't nobody standing like that.
कदी गलियां नपे कदी हंस के कलेजा मांग दिया.
They connected through the dancing. That's the magic of dancing. When you're touching, when you're getting that close, lift it up in the air and that. Eiffel Tower in the back, lighting, glistening and that. I knew it was Paris. Yay! She didn't just. But
नशे सी चढ़ गई ओए पतंग सी लड़ गई ओए
Yay!
नशे सी चढ़ गई ओए कुड़ी नशे सी चढ़ गई.
Oh God. It seems like an interesting movie about love and that. Seems interesting. What's your
Creo que me está engañando con su asistente. Esta noche, tú y yo nos vamos de cacería.
Soy Darío.
Okay, so let's have some details of this updating process called error matrix method, EMM. Before having this detail, I would like to let's say discuss a little bit some operations with matrices. Okay, now let's consider to have a matrix A. Okay, and this matrix is a square matrix, maximum rank matrix, and therefore what we can say is that if we have this operation between matrices, the inverse of A times the A itself is of course equal to the identity matrix. Okay, now if the matrix A depends on a parameter, let's call it alpha, okay, then we can think to take the derivative of the matrix A, so A depends on alpha, and therefore we can think to have the sensitivity of this matrix product like this. Okay, and of course that sensitivity is equal to 0. But if we have the definition of that, we can say that that derivation sign could be explicit just by having the dA to the -1 with respect to alpha times the matrix alpha itself plus the matrix to the power of -1 and then the derivative of the matrix alpha with respect to alpha, and that is equal to 0. Because of that, what we can say is that the derivative of the inverse of a matrix with respect to a parameter could be written as negative the inverse of the matrix A times the derivative of a with respect to alpha times the power of alpha to the negative 1. Okay, so that is the property, the algebra property of whatever matrix A that could be used to perform the previous orthogonality condition. Okay, so having said that, let me consider that you are having your, let's start with the mass matrix, your numerical mass matrix, then you have your experimental mass matrix, okay, and according to the error matrix method, you can say that your numerical matrix plus your error mass matrix delta m, okay, is giving me the exact experimental mass matrix, okay, if I am finding out the error matrix method, okay. But now if I so the task is to find out this error matrix delta m, okay. Now if a series expansion is performed in the neighborhood of the generic parameter alpha, that is your parameter, that is your updating parameter, if you will, of this inverse of the mass matrix n, okay, one has this very nice expression, okay. Let me write that before what we got. So we have the experimental mass to the -1 could be thought as the series expansion, okay, of my numerical mass matrix, the power -1, plus, okay, the derivative, okay, so the numerical mass matrix to the power -1 with respect to the parameter alpha, that is numerically evaluated by the change of your parameter alpha, okay, plus what we can say higher order terms, just first terms, okay. Then we keep going on that expression, that is equal to numerical, sorry, mathematics to the power of 1, and then we recall what is the meaning of the, how can we write better, the derivative with respect to a parameter alpha of the inverse of a matrix, and therefore we can substitute the result that we already had. Sorry. Okay. And then delta alpha. Okay, oh, sorry. Okay. Plus higher order terms. And therefore, what we can have is that your equation could be written as this one, negative minus 1. Now this derivative is just the error difference between a finite difference way, is the delta m times your numerical mathematics to the power. Okay, and as a result, what we can write is that your error mathematics from the previous equation could be rewritten as your numerical mass matrix times the difference of your numerical inverse of the mathematics negative the experimental inverse of your mathematics times your numerical mathematics. Okay, please note that by recalling the orthogonal conditions, okay, by recalling that your whatever modal mathematics numerical transpose time your numerical mathematics time the same numerical modal max is equal to the identity, and the same your experimental modal mass transpose times the experimental mathematics times your experimental modal masses is once again identity matrix. We can say that your inverse of the numerical matrix mathematics is practically your numerical mode shapes times your numerical mode shapes matrix transpose, and the same your experimental mathematics to the minus 1 is practically your experimental modal matrix times your experimental transpose of your modal matrices. Okay, and these, by the way, are called pseudo inverse matrices. Okay, please note that the rank of both the mass matrix to the minus 1 and the stiffness matrix to the minus 1, okay, is equal to the number of modes. Okay, so it is not equal to the number of degrees of freedom that we consider. Okay, using the same approach, okay, please note okay, using the same approach, what we can write is that your error stiffness matrix could be expressed as your numerical stiffness matrix times the difference of the inverse of the numerical stiffness matrix with respect to the experimental stiffness matrix, okay, times your experimental stiffness matrix. Okay, oh, sorry, numerical. Sorry. Okay. And once again, we can, as by considering the orthogonal conditions of the stiffness matrix with respect to the shape with respect to the stiffness matrix better, what we can say is that the inverse experimental stiffness matrix is practically given by the product of the experimental Bosch matrix times the diagonal matrix of the eigenvalues to the power of -1, okay, the inverse, times the modal experimental matrix, okay, and the same for the numerical inverse stiffness inverse matrix. It is equal to the numerical Bosch matrix times the diagonal numerical eigenvalue matrix times the numerical modal mass and mode shapes matrix. Okay. By the way, the diagonal lambda matrix is the matrix who's having 1 over omega 1 square, 1 omega 2 square, up to 1 over omega number of modes that are considered square. Okay, just to be sure. So that is your step 1. Let me write it somewhere. Here we go. So step 1. Step 2. Once we got the error stiffness and mass matrix, we have just to update your numerical mass and stiffness matrix. Okay. So once a possible modelization error area has been estimated by delta kappa and delta m, then the new spatial model is given you by what we already wrote. Ku is your numerical model plus your delta k, and mu equal, updated, is equal to the starting point numerical mass matrix plus this delta m, delta error matrix, okay, delta mass matrix. Okay. Once again, the information that your error matrices delta k and delta m are telling you is possible area in your finite model that requires attention in the sense that we need to have information concerning, let's say, a new material definition or discretization, or let's say some balls or free plays or joints need a better representation. But also maybe if you think, for example, whatever structure, maybe there are some areas in which thicknesses, for example, are not well understood numerical with respect to the experimental one, and therefore these delta k and delta m are we to inform you what are these area that requires a better finite element model. Once you got this information, then you can update your stiffness and mass matrices like that, just by applying the equation that I just drew. Okay. In this way, it is clear that the choice of the parameter alpha, that is the design parameter for updating, is of paramount importance, because if you fail to identify the right parameter, then maybe your updating process will not converge, will not have any useful information. Just to give you an example, if you are having, for example, a structure for which the thickness definition is not properly given for a specific area, and your design parameter for updating, is your parameter alpha, is not describing that thickness, but maybe only, for example, the, the value of the Young modulus, then you can have a wrong identification of this delta K and delta M. And therefore, the final result is a bad one, because you can't have a good idea, or therefore you can't have an updated, truly updated stiffness and mass properties. Okay, therefore it is up to you as the test engineer and numerical experimental correlation engineer that is defining, that is looking for the right parameters, and that is a very sensible operation that you have to do. Once you define the right parameters, then your updating process will give you the right answer. On the contrary, you can stay years trying to update your numerical model, but there is nothing to do. Okay, I always have this example, and compared to that, there is also another issue, that these formulas are good if there is a first order approximation. Okay, so if your numerical model is really too far with respect to the experimental one, then there is nothing that you can do, because the first order approximation could not be could not be used to represent the actual reality. And just to give you another example, it is just as we would like to have a Ferrari car just by starting with a Fiat 500 one. Okay, so you can't have this transformation of the 500 car into a Ferrari car. Okay, just because they are too different, too far away from each other. Okay, so in the updating process, the first thing is that these models, American experimental, should be quite close, and the previous analysis, the previous evaluation of the correlation between numerical and experimental model is fundamental. If that correlation is good, then you can go with the first order updating process, like the one that we discussed so far, that is the Evermatics method, EMM. Okay, and the second step is that you have to find out the right parameter for a leader, the right alpha. Please note that it should not be only just one parameter. That could be whatever number of parameters. For example, the thickness in an area, the Young modulus in another part, let's say the cross section of the road in other point of the structures, and so on. Okay. So it is just to remark that. First, let me write that in red. Design parameters for updating are fundamental. Numerical and experimental models should be quite close to one each other. Okay, that is small delta Fn I values of the MAC. Okay, just to give you an idea. Another point is that sometimes EMM, this method, does not converge. Okay. What does it mean that? It means that this first order approximation is not good enough to have the updated numerical model in terms of mass and stiffness matrices. In this case, what we can say, we can say that we can iterate the EMM algorithm okay, so that for example, your updated stiffness matrix of the iteration step I is given you by the updated stiffness matrix at the iteration step I -1, so at the previous one, plus the delta K error matrix at the iteration step I iteration step. And also for the mass at the iteration step I could be expressed in terms of the what we got at the previous iteration step plus the actual iteration step. What does it mean that? It means that once we got your updated of the stiffness and mass matrix at the given ith iteration step, then we solve for the new eigenvalue problem, and therefore we can evaluate the new delta K and delta M matrices. Okay, and with that we can have the new updated one. Please know that convergency is not guaranteed. Okay, and that is one of the major issues of this method. But indeed, all the updating methods are not guaranteeing you your the convergency. So it is always let's say a nightmare if you start updating your numerical model. If you start from scratch, if you don't have any other previous information about the numerical model. Okay. Okay, that's it. Oh no, the last point, sorry, the last point, the error matrix method, EMM, okay. What's wrong here? Okay. Is not including any rigid body motion. Okay, that's because the rigid body motion has a zero natural frequency by definition, and therefore we can't perform could not be evaluated. Okay, because if you are setting the diagonal term equal to 0, then you can't have the inverse of that diagonal eigenvalue matrix. Okay, so you can't include those rigid body motion. You just have to include the true elastic body motions, elastic motions. Okay, more shapes with frequency, natural frequency that is different from 0. Questions on these methods, the error matrix method? Okay, if there are no questions on that, let me introduce a second method for the structural updating, and this method is quite different in a sense because it's not considering the correlation, the comparison and therefore we can't have the structure updating using the modal base information in terms of modal parameters, shapes, and natural frequencies. But indeed, it uses the frequency response factor. So it is based on the response model. If you remember, if you go back to your notes, you can easily find out that something at a certain point I said you that the comparison could be carried out also using the response model. Okay, now this new different updating method is using such response model to update the structure. This method is called predictor corrector method. Sorry, predictor corrector method. Okay, PC. Okay, for once again structure updating. Okay, such a method is based on sensitivity analysis. Okay, with respect to changes of some design parameters that are useful for updating. Okay, and the correlated the comparison is carried out considering the response model that is your FRFs. Okay, let me see how we can have your this comparison. Okay, in order to do that, let me introduce two correlation functions. The first one is your chi shape S, that is a function of the running frequency omega, and this chi S shape, okay, is defined as the ratio of the amplitude of the product of your experimental FRF emission times your numerical FRF, okay, in amplitude square, whereas the denominator of that is your experimental FRF emission times your the same experimental FRF times your product in the product of the numerical FRF emission omega times the numerical FRF. Okay, please know that when I'm writing that means permission. Operator. Okay, that is the shade correlation function between the FRF. We get also another correlation function that is relating the amplitudes, your Ki, that is amplitude. Okay, of omega, and this is equal to the ratio of twice the amplitude of the same linear product of the experimental emission FRF times your numerical omega, okay, amplitude, divided this time the inner product between the experimental FRF emission times your experimental FRF plus your H numerical emission times your numerical FRF as well. Okay. Okay. So these two are the correlation functions that we can say. The first one is derived from the Cauchy-Schwarz inequality, okay, from the Cauchy-Schwarz inequality between complex numbers. Okay, so H experimental, whatever is your omega emission times your H numerical, okay, in amplitude is always less than the product of these two quantity amplitude. Sorry. Like this, okay. And the other one is Ki is derived from this inequality to the distance, okay, into complex number A and B. Indeed, if you do that, you get A squared plus B squared is larger than 2AB, okay, and then it comes to 2AB divided by A squared plus B squared is less than 1. So at the very end, what you got is that both chi s and chi a are quantities, are functions that are defined in a 0-1 range, okay? And 0 means that these quantities are not correlation at all, whereas 1, when these quantities are even 1, we are having a perfect correlation. Okay, according to their definition. The A means for the amplitude and the S means for the shape. So chi S, that is for the shapes, okay, gives a measure of the correlation between FRFs by taking into account the shape and the peak, sorry, distribution of the FRF. Okay. On the contrary, your Ka, your correlation function that refers to the amplitude, is just taking into account the scaling between the FRFs. Okay, so these two correlation functions operates in a quite similar way, but the first one is giving you information about the peak distribution, the shape, whereas the second one just the scale. And that's the reason why the predictor corrector method is using both of these two correlation functions. Okay, just a last word on this. Please know that we can have whatever FRF matrix it is. We can have your system that is excited using, let's say, a multiple input. We are having multiple outputs. So your FRF, your H, is a full matrix dimension, number of input, number of outputs, better number of output times number of input. Okay, and here in this formulation, what we are having is that we rearrange this full FRF matrix in a sort of column vector. Okay, and this column vector is having this column vector is having the components that are referring to the degrees of freedom pairs, and each vector is evaluated for each value of your omega. Okay, and that's the reason why we can write the expression of the Chi-S and Chi-A in the way that we do. The second important information that this predictor corrector method is introducing is a different way of introducing possible errors in your final element moment. You remember in the previous method, the error matrix method, we introduced error by the error matrix delta K or delta N. Okay, and because these two matrices are representing actually the difference between the experimental and numerical one by definition, the error matrix is just telling me that the components of this error matrix that are different from zeros are representing the values and the area in your structure that requires refinement for your structure updating. Okay, in this approach, in the predictor corrector method approach, the design parameters for your finite element method are defined so that you are considering your stiffness matrix as a combination from, let's say, I that goes from 1 to number of elements of your, let's say, Li times your elemental stiffness matrix I, and your mass matrix could be represented as the same combination from 1 to the number of elements, okay, of Mi elemental mass matrix I. Okay, so this is what we call the p-value formulation in the structure updating methods for which you can identify those parameters lower m as those parameters that could represent possible deviation from the actual reality of your numerical model. From the starting point, of course, your Li and Mi elements are all equal to 1. That is, your finite element model is composed by a number of elements of elemental stiffness that are all combined together, okay? And each element is combined together having weights equal to 1. By introducing this updating method, we would like to change those weighting parameters. So you are going to change your Li and Mi in order to introduce possible deviation in your finite element model in order to take into account the experimental findings, okay? So we generally define a vector P, and that is why we value that as the p-value formulation, as the vector in which we had all the Li and all the Mi, okay, coefficients that we introduce when defining the overall stiffness and mass matrix. Of course, the dimension of this p vector is 2 number of elements, okay, times 1, okay, and that is the vector of the unknown design parameters for structural updating. Okay, using this p-value formulation. Okay, so having said that, we have the correlation function, the chi functions, chi A and chi S, and then we have the unknown design parameters, P, that is a collection of the L that are referring, for example, to the mass matrix, to the stiffness matrix, and the M that are referring to the mass matrix. Okay, so in order to have the updating of your structure, we would like to have possible information of one design parameters concerning the change of the correlation function. Okay, so it is possible to evaluate the effect of a change of a parameter let's see, delta pi, okay, to the global correlation functions chi A of omega and chi S of omega. How can we do that? By using a Taylor series expansion. What we got is that, for example, regardless the type of correlation function could be either A or S, the modify chi at a given frequency omega bar, okay, is equal to the reference, the initial value of the corresponding index at the same bar frequency plus the derivative of such a chi function with respect to the design parameter pi, okay, times the change of such a parameter. Okay. Now, if we consider if the previous equation is sought as a search, okay, for the updating parameter, what we can say is that your modify chi function should be equal to 1, because when we are having the correlation function equal to 1, that even frequency, then it means that we have updated your structure, okay? And of course, your initial chi function, at a given frequency omega bar, okay, is the actual correlation between your experimental and numerical models. Okay? So, just to give a more general equation, considering all the frequency lines that are available in our analysis and all your design parameters for updating, we can rewrite the previous equation as this general equation. So, like this, omega 1 with respect to P1, the chi s omega 1 once again, so over the P2 up to chi s omega 1 over P and M. Oh, sorry, many times. Okay, and M. Then what we got here is the chi s omega 2 over the P1, the chi s omega 2 over P2, the chi s omega 2 over P and M. Okay, up to the last line, the chi s omega number of frequency lines with respect to P1 first parameters, up to the chi s omega number of frequency line P and M. Then we go down until the Ka P1 omega and F, Ka omega and F, P and M. And that is a very large matrix like that. Sorry. That is multiplying your design parameter, change of the design parameter, delta P, delta 2, okay, up to delta P and M, and that is equal, next line, to the error, okay, that is 1 negative chi S omega k for the kth omega line, 1 negative omega ka, sorry, omega k line. Okay, that is, we can write in a more compact form as your sp times delta p equal to epsilon. Okay, oh sorry, vector and vector here. Okay, and that is your sensitivity matrix. Whose dimension are, of course, number, twice the numbers of frequency lines times the number of design parameters for updating. Here is a vector equal to number, dimension number of design parameters for updating, and once again the residual terms in which we are having the, once again, a vector column vector equal components equal to the number of design parameter for updating. Please note that the number of frequency lines is generally much larger than the number of design parameters for updating. Okay, so that's it for today. Tomorrow we will end these predictor corrector methods for structure updating. Do you have any questions in this? Okay, if not, thank you for your audience, for attendance, and see you tomorrow, same times. Okay, same time. Thank you, bye.
Professore, scusi,
Sì,
avrei una domanda sulle date degli esami,
sì.
perché ho visto che su Infostud, diciamo, le date del suo esame corrispondono tutte quante con le date dell'appello di Elasticity del professor Mastroddi, ma diciamo, si può fare qualcosa perché sono tutte le stesse date, sia della sezione di invernale che estiva. Non
Allora,
si può-
guarda, io queste date qui le ho prese dal consiglio d'area, cioè me le hanno date loro,
Ah, ok,
quindi io non ho deciso nulla.
certo.
Quindi mi hanno dato quelle date e le ho inserite.
Mhm.
Quindi fate un'email al professor Franco Mastodi, peraltro, che fa anche Elasticity, in cui gli fate presente questo problema. Dal mio punto di vista, se si può cambiare, insomma, non posso
Va
cambiare.
bene, allora, dato che dopo c'è lezione col professor Mastroddi, magari provo a dirlo a lui direttamente.
Fatelo presente, sì. Ok.
Grazie mille.
Prego. So your colleague is asking about the final exam dates that are overlapping with another exam, Elasticity 1. So what I reply to that is that those final exam dates are dates that were given to me from the council. So if there is a chance of changing those dates, it's okay for me. So just email Professor Mastroddi in order to discuss this topic. Okay. Very good. So if there are no other questions, thank you very much and see you tomorrow. Bye bye.
Arrivederci.
Arrivederci.